In this video, we are going to be covering section 3.2, which is going to be over quadratic functions. It's also going to be over power functions and polynomial functions as well, but we are just going to start out talking about quadratic functions, which are, of course, a particular kind of polynomial function. In particular, they are a degree 2 polynomial function. So a quadratic function in general form is going to look like f of x equals ax squared plus bx plus c, with a different from 0. Of course, we require that, so we have a legitimate quadratic function. You know, if a is equal to 0, then we're just looking at a linear function instead. And a, b, and c are just the constant coefficients. So that's the general form. Another form that we're going to be interested in is going to be the vertex form or the standard form of a quadratic function. And this looks like f of x equals a, and then in parentheses times x minus h squared plus k, where h comma k is going to be the vertex of our quadratic function, which is going to correspond to either the lowest point on the graph of our quadratic function or the highest point on the graph of our quadratic function. And so we can find the vertex of a quadratic function in the general form by using completing the square on f of x in the general form, or instead we can use the following formula for the coordinates of the vertex. So the vertex is going to be at minus b over 2a. Again, we're thinking about starting out with a quadratic function in general form. So here, a and b are just going to be the coefficients in front of the degree 2 term and the degree 1 term, respectively. So the x-coordinate of the vertex is going to be equal to minus b over 2a. In other words, h is equal to minus b over 2a. And the y-coordinate of the vertex is just going to be f of minus b over 2a. So k is equal to f of minus b over 2a. And so the graph of a quadratic function is called a parabola. Which is going to look like either an upwards facing like u or a downwards facing u. So if a is greater than 0, the parabola opens up. And if a is less than 0, the parabola maybe instead of saying opens, we'll say faces upwards. And if a is less than 0, the parabola faces downwards. Okay, and so the domain for all quadratic functions is just going to be all real numbers. So we could write our fancy R to say all real numbers, or we could just write the interval. We put more minus infinity to infinity. Same thing either way. And then the range, so if a is greater than 0, well, then the lowest point on the graph of our parabola is going to be the vertex. And so since a is greater than 0, the parabola is going to be facing upwards. So our right endpoint for the range is going to be infinity. And our left endpoint is going to be the y-coordinate of the vertex, so f of minus b over 2a. And since the graph of our parabola will go through its vertex, we do include the left endpoint of the range here. And if a is less than 0, well, now the right endpoint of our range, so the highest point on the graph of the parabola, is going to be the vertex. So the right endpoint of our range when a is less than 0 is going to be included, and it's going to be f of minus b over 2a. And our left endpoint, well, since it's just going to be a parabola facing downwards, that's just going to extend downwards indefinitely. This means the left endpoint of our range is going to be minus infinity. All right. And then here below, we have a graph of a parabola. So the graph in blue is the graph of the quadratic function f of x equals x minus 2 and then squared and then minus 4. So here we're looking at the formula for the quadratic function in the vertex form. And so we can read off the coordinates of the vertex directly from this form. Is going to be 2, negative 4. And of course, that is where the vertex is. It's at the point 2, negative 4. And as we can see, so here a would be 1, so that's a positive number, so greater than 0. So we have an upwards facing parabola. And so the vertex is the lowest point. And so we can see that the range would be negative 4 to infinity. All right. Okay, so in these examples, we are going to sketch a given function, and we are going to then label the intercepts and find the domain and range. All right, so in the first of these examples, we are given the quadratic function f of x equals minus 1/2, and then parentheses times x plus 1 squared minus 3. And so the first thing that we can notice here is that this quadratic function is already in the vertex form, so we can read off the coordinates of the vertex directly from the rule of assignment for our quadratic here. Again, the vertex form looks like f of x equals a times x minus h squared plus k. So since we have x plus 1 squared, that means h is going to be a negative 1. And then since we have minus 3 over here, that means k is going to be negative 3. So our vertex is going to be at the point negative 1, negative 3. Which is going to be over here. And then, so the leading coefficient a is negative 1/2, which is less than 0, meaning that our parabola is going to be downwards facing. And so since the vertex, which is going to be the highest point on our parabola in this case, since it's a downwards facing parabola, since it lies below the x-axis, that means that this parabola is going to have no x-intercepts, or this function f is going to have no x-intercepts. And then for the y-intercept, so we can set x equal to 0. So f of 0 is equal to -1/2 times 0 plus 1 squared in parentheses, and then -3. And so this is going to be equal to, well, we'll have 1 squared, which is going to be 1, then times -1/2 is going to be -1/2, and then -3. So this is -3.5, or in other words, since 3 is the same as 6/2, -7/2. So this is going to be about right here, just between -3 and -4 on the y-axis. And then by symmetry, we know that the value of our quadratic function f here, when x is equal to -2, is also going to be -3.5. So we got at least 3 points that we can use to go ahead and kind of sketch our graph. Okay, so let's label the one intercept, which is only going to be the y-intercept. Again, this is going to be the point 0, -7/2. And let's go ahead and label the vertex too, anyways, just because, even though the instructions don't tell us to, we will. So this is going to be -1, -3. Okay, and then we already said, so the domain for all quadratics is going to be all real numbers. So this was for our y-intercept. And then domain and then range. So again, since a is less than 0 here, that means that the right endpoint of our range is going to be the y-coordinate of our vertex, so -3. And the graph of our parabola does go through the point -1, -3, so -3 is included in the range. And then the parabola just extends downward indefinitely. So we're going to have from -infinity to -3 for the range. Okay. And then for our second of these examples, we are given the quadratic function f of x equals 4x squared plus 8x minus 1. So this time our quadratic function is going to be in general form, as we can see. So if we want to figure out what the coordinates of the vertex are, we are going to have to use the formula for the vertex. So this is going to be A is equal to 4, B is equal to 8, and we don't really need this for the formula for the vertex, but let's go ahead and mention that C is equal to -1. So those are just the coefficients for our quadratic in general form here, 4, 8, and -1. And so for H, the x coordinate of the vertex, so H is going to be equal to minus b over 2a, which here is going to be minus, and then an 8 for b, and then over 2 times 4 for a. So this is equal to -1. And then k is going to be equal to f of -1. So we want to evaluate our quadratic at x equals -1. So f of -1 is going to be, well, 4, and then times -1 squared, plus 8 times -1, then -1, which is equal to, well, -1 squared is going to be +1, so we have 4, minus 8, -1, so we have 4, minus 9, which is going to equal -5. So our vertex is going to be the point -1, -5. Just going to be right here. And so this time, our quadratic is going to be an upwards facing parabola, right? Because a is equal to 4, so it's a positive number. So we have a is greater than 0. So we know that our quadratic is going to be an upwards facing parabola, so we will have x-intercepts here. Since our vertex is below the x-axis and this parabola is going to open upwards. First, let's worry about the y-intercept. So for the y-int, we just have to evaluate f at x equals 0, which when it comes to a quadratic function in the general form is quite easy because, as we can see, since the other terms in the general form involve an x, when we plug in 0 for x, all those terms are going to become 0, and all that we're left with is c. So we're going to have 4 times 0 squared plus 8 times 0 minus 1, which is just going to equal -1. So we have a y-intercept at 0, -1. Okay, and then for our x-intercepts, we can use the quadratic formula. So we would take our quadratic function and set it equal to 0, which is going to give us the quadratic equation 0 equals 4x squared plus 8x minus 1. And then we would plug our numbers for a, b, and c into the quadratic formula. So according to the quadratic formula, x is equal to minus 8, that's minus b, plus or minus the square root of b squared, so 8 squared, minus 4, and then a is going to be 4, and c is going to be minus 1 over 2a, so over 2 times 4. And when we go and simplify this, well, we are going to have minus 8 plus or minus the square root of 64 plus 16, so square root of 80 over 8. So in other words, we have minus 1 plus or minus the square root of 80 over 8, which is going to give us two solutions for x. X is going to be approximately negative 2.118 for one of our solutions, and for the other solution, we are going to have x as approximately 0.118. So again, we just got these approximate values from the quadratic formula. If we go through and simplify this, what we are going to end up with is going to be minus 1 plus or minus square root of 5 over 2. So let me write that over here. Minus, see if we have room. Minus 1 plus or minus the square root of 5 over 2. So that would be the exact value for our zeros to this quadratic equation, which are going to give us the x coordinates for our two x-intercepts. And these are the approximate values. So approximately, we will have like an x-intercept like right here, very close to the origin, and then we will have our other x-intercept over here. So this is negative 1, negative 2, so just to the left of negative 2. Okay, so let's go ahead and sketch our graph here. And label our intercepts along with the vertex. So we have this x-intercept, which is going to be minus 1 plus square root of 5 over 2, comma 0. Then our other x-intercept, which is going to be at minus 1 minus square root of 5 over 2, comma 0. Then we had our vertex down here at -1, comma -5, and our y-intercept over here at 0, comma -1. And let's try to squeeze in. So the domain, trying to find a spot to put that. So I'm just going to say D is going to be all real numbers once again, so minus infinity to infinity. And for the range, well, since this is an upwards facing parabola, the left endpoint of our range is going to be the y-coordinate of the vertex, because it's going to be the lowest point on the graph of our parabola. And then the right endpoint of our range is just going to be infinity. So our range is going to be from -5, with the endpoint included, to infinity. All right. On to our next set of examples. So in our next set of examples, we want to find the rule of the quadratic function that has the given vertex and passes through the given point. So here we are going to want to use the vertex form for a quadratic function. We can almost think about it as being, say, like the point slope form equivalent for quadratic functions. In particular, in the sense that oftentimes the first equation we are going to be able to write for a quadratic function is going to be the equation in the vertex or standard form. So again, the vertex form, it looks like f of x equals a times x minus h squared plus k. So in the first of these examples, we are told that the vertex is going to be at the point -3, comma 2. So this is our h, comma k for the vertex. And it passes through the point 2, comma 1. So we are going to use this information to solve for a. So the first thing we can do is say, okay, our quadratic function is going to look something like f of x equals a times x minus a -3 squared plus 2. Or in other words, f of x equals a times x plus 3 squared plus 2. And now we want to solve for a. So we are going to plug in for x a 2, and for f of x, we are going to plug in a 1. And this is because since our parabola passes through the point 2, comma 1, well, this means that for our quadratic function corresponding to this parabola, f of 2 is going to be equal to 1. So we're going to say f of 2 equals 1, implies, so a little implication arrow, if you will, that we have the equation 1 equals a and then parentheses times 2 for x plus 3 squared plus 2. All right, so now we have an equation that we can use to solve for a. So let's start out by simplifying on the right. So we have 1 equals a, and then 2 plus 3 is going to be 5. So we have a times 5 squared plus 2. And we'll continue to simplify. 1 equals a times 25, or 25a plus 2. And then we want to start solving for a, so we're going to subtract 2 from both sides. And we're going to get minus 1 equals 25a. And so a is equal to, after we divide both sides by 25, minus 1 over 25. And so for our final answer here, now that we know our value for a, is going to be that our quadratic function is given by the formula f of x equals minus 1 over 25, then parentheses x plus 3 squared, and then plus 2. All right, so now we want to do the same thing, except here in example 2, we are told that the vertex is going to be negative 2, 0, and our quadratic function, its graph is going to pass through the point negative 3, 1. So this is our h, k. And this is our x, f of x. All right, so using just the formula for the vertex form, we'll just plug in h and k. So we'll have f of x equals a. We'll still have to solve for that. And then parentheses times x minus a negative 2 squared. And then plus 0 for k. So we can go ahead and simplify this and write f of x equals a times x plus 2, because we have the double minus in the parentheses, squared. Okay, and then we have to solve for a. So since our quadratic function passes through the point negative 3, 1, this means that f of negative 3 is equal to 1. So this tells us that to solve for a, we have the equation 1 for f of x equals a, and then parentheses, and then minus 3 for x, plus 2, and then squared. So we can simplify 1 equals a, and then we have minus 3 plus 2 is going to be minus 1 squared. And then minus 1 squared is, of course, just 1, so we end up with 1 equals a. So f of x is equal to x plus 2 squared. Okay, moving on with our examples. So in the next few examples, we are going to be looking at some word problems involving quadratic functions. So in this first example, we are told if an object is thrown upward, dropped, or thrown downward and travels in a straight line, subject only to gravity with wind resistance ignored, the height h of the object above the ground in feet after t seconds is given by the quadratic function h of t equals minus 16t squared plus v naught times t plus h naught, where h naught is going to be the height of the object when t is equal to 0, so the initial height of the object, and v naught is the initial velocity at time t equals 0. And we are going to say that the value v naught is taken to be positive if the object moves upwards, so if it was thrown upwards, and negative if it moves downwards, so if it was thrown downwards. Okay, and so given this, we are told to suppose that a golf ball is thrown downwards from the top of a 625-foot high building. So 625 feet is going to be our initial height. This is going to be our h naught. With an initial velocity of 65 feet per second. So since it's downwards, that means v naught is negative. And since the initial velocity is 65 feet per second, this means that v naught is going to equal a negative 65. And then we're asked, so given all this information, how long does it take to reach the ground? So the first thing we are going to do is just write our function h of t, which is going to give us the position of the golf ball after t seconds. So h of t, according to all the information we are given, is going to be equal to minus 16t squared plus, or sorry, minus, because v naught is a minus 65, minus 65t plus 625. Okay, and so it's asking us how long does it take to for the golf ball to reach the ground. So essentially we are trying to find when h of t is equal to 0. So what we are going to do is set h of t equal to 0. So we have 0 equals minus 16t squared minus 65t plus 625. Okay, and so we can go ahead and just plug, since now we have a quadratic equation with all the non-zero terms on one side and 0 on the other, we can go ahead and use our values for a, b, and c in the quadratic formula. So we have a is equal to negative 16, b is equal to minus 65, and c is equal to 625. All right. And so, according to the quadratic formula, t is going to be equal to a minus 65 plus or minus the square root. We're going to have a lot under the square root here of minus 65 squared minus 4 times negative 16 for a and then times 625 for C over 2 times negative 16. And so when we simplify this, what we end up with is 65 plus or minus, and then under the square root we have 44,225 over minus 32. So this isn't simplified as much as possible. Of course, all we did was just cancel out the double minuses at the front in the numerator here, and then just simplified what we had under the square root. And for the approximate solutions, we get t is approximately minus 8.6 or 4.54. And here, so we do have two solutions. We have a negative one and we have a positive one, but we want to think, okay, so we're being asked how long does it take to reach the ground? And here t is time since we've thrown the ball downward. And so, you know, we aren't really thinking that we are going to travel backwards in time, so we want to ignore the negative solution here and only focus on the positive solution. So the ball will reach the ground after approximately 4.54 seconds. And by the way, not sure if I've mentioned this before, but if you ever see like the wavy equal sign, all that means is, you know, it's an approximation. It's not like t is exactly equal to this value. Okay, moving on to our next example. So in the next example, we are told a backyard farmer wants to enclose a rectangular space for a new garden within her fenced backyard. And she has purchased 80 feet of wire fencing to enclose 3 sides and will use a section of the backyard fence as the 4th side. And so it wants us to find a formula for the area enclosed. And then on top of that, we want to then use the formula to determine what dimensions she should make her garden to maximize the enclosed area. All right, so the first thing that I think we should do here is try to come up with a sketch of the situation. So let's go ahead and say, okay, this in pink is just going to be the backyard fence. Okay, and then in purple, we will do the wire fencing. So it's a rectangular region that she's trying to enclose, and she's going to use as one of the sides the backyard fence. So we'll just sketch a rectangular region that uses the backyard fence as one of the sides. And so we can call these two congruent edges the widths. And we can call this other edge the length, but we can also come up with a formula for this length in terms of the widths. So since she has 80 feet of wire fencing to enclose this rectangular area, and she wants to use all 80 feet of it, this means that the length is going to be 80, so the amount of feet she has, and then minus however much fence we use for the other two sides. So 80 minus 2W. Okay. So we can say that this is L, the length. All right, and so for the area, well, the area of a rectangle in general is just going to be the length times the width, or the base times the height, however you want to think about it. So here we're thinking about length times width. And then if we want to have a formula for the area in terms of only W, well, we can use the fact that we realize that L is going to equal 80 minus 2W to rewrite L as 80 minus 2W. So our formula for the area enclosed is going to be given by the function a of W, which equals 80 minus 2W, and then times W. And we could rewrite this as, so distributing the W over the two terms and kind of rearranging things so that we have the higher degree term first, minus 2W squared, and then plus 80W. All right, so here we have a quadratic expression, and we can see, so the leading coefficient A is going to be less than 0. We have a -2 there. And so this means that to find what dimensions she should make her garden to maximize the enclosed area, well, we can find the value of W that will maximize the enclosed area by just determining what the vertex for this quadratic expression is, because that is going to give us the highest point on the graph of this parabola here, minus 2W squared plus 80W. So A is going to be -2. B is equal to 80. Okay, and then according to our formula for the vertex, H is equal to minus B, so minus 80 over 2A, so over 2 times -2. So this is going to be equal to 80 over 4, which is equal to just 20. So the value of W that's going to maximize our area here is going to be 20. So for the dimensions, to maximize the enclosed area, well, we are going to want the width, so W to be equal to 20, and we are going to want the length, well, it's going to be equal to 80 minus 2 times 20. which is going to give us 40. And this is in feet, so 20 feet and 40 feet. So that's how we're going to use up all 80 feet. We're going to have 20 feet for these two sides and 40 feet for this side. And not that we care too much, but this is going to give us an area, an enclosed area of 800 square feet. And if we think about, you know, kind of other values of W, like we could think, well, what if we made W 10? Well, then we would have 10 for the width, and we'd have 80 minus 20 for the length, so 60 feet. So we would have 10 by 60, which would give us 600 square feet for the area. So that's less than 800 square feet. And we, you know, so using a value less than 20 doesn't seem to work. So we could look at a value greater than 20, such as using 30 feet for the widths. And in that case, well, we would have that W is equal to 30 feet, and L is going to equal 80 minus 2 times 30, so 80 minus 60. So L would be 20 feet. So for the enclosed area, since it would be 30 by 20 feet, it would be 600 square feet. So again, it's less than 800 square feet. All right, really quick, we are going to be talking about factoring quadratics. Of course, you can always use the quadratic formula to find the factors for a quadratic expression, ax squared plus bx plus c. But the quadratic formula can be a little bit tedious to use at times. While this method that we are going to talk about doesn't work for all quadratic expressions, it does work for any quadratic expression that is factorable over the integers, meaning that when we look at the two binomial factors, say like ax plus b times b plus cx plus d, a, b, c, and d would all be integers. So that's kind of what it means for a quadratic to be factorable over the integers, is that we end up with those sorts of binomial factors. And this corresponds to the quadratic having only rational zeros. And so we are going to quickly talk about this method for factoring quadratics that can be faster than using the quadratic formula when possible. So it's called the AC method. And to factor a quadratic of the form ax squared plus bx plus c using the AC method, so assuming it is factorable over the integers, we want to multiply a and c and then consider factors m and n of a times c, so the product, that add to b. So once we find two factors m and n, whose product is equal to a times c, we can then substitute n plus m in for b, because we also we require n and m to add to b. And then we can go and proceed to factor the polynomial by grouping. So if we start out with ax squared plus bx plus c, then we want to look at the product a times c and consider all the different factorizations of a times c into exactly two factors. And then we want to find which factorization gives us two factors whose product is not just a times c, but also whose sum is n plus m. And once we find those two factors, n and m, we can decompose the middle term, b times x, and instead write ax squared plus n plus m times x, and then plus c. So this turns our trinomial quadratic expression into a four-term quadratic expression. So we'd have ax squared plus nx plus mx plus c. And then the way we would group is we would group either of the linear terms with the degree 2 term, and then the other linear term with the constant term. So we could do ax squared plus nx plus mx plus c. And then from here, what we want to do is pull out the greatest common factor from each grouping. And when we do that for both of our groupings, where the groupings that we're referring to here are the two terms in the parentheses, once we do that for each of our groupings, we should have the same expression remaining in the parentheses. So that'll be one of our binomial factors. And then what we've pulled out as the greatest common factor from each group, from each of the two groupings, is going to give us the two terms for our other binomial factor. And so on top of the AC method, we have a few different formulas that will also help us factor some quadratic expressions quickly. So if we ever have a quadratic expression of the form a squared minus b squared, then we can use the difference of squares factorization formula. So a squared minus b squared is equal to a plus b times a minus b. And then we also have the perfect square factorization formula. So if we ever have a quadratic expression of the form a squared plus or minus 2 times a times b plus b squared, we can use the formula a squared plus or minus 2ab plus b squared is equal to a plus or minus b and then squared. All right, so let's look at factoring some quadratic expressions. So for our first example, we are given the quadratic expression x squared plus 11x plus 24, and we want to factor this into its two binomial factors. If we look at our two special factorization formulas, the difference of squares and perfect square factorization formula, the quadratic expression that we have here doesn't resemble a difference of squares, and it doesn't resemble a perfect square, so we're just going to use the AC method. So let's say what a, b, and c are. So a is 1 since we have just x squared, b is 11 because we have 11x, and c is 24. So a times c is equal to 1 times 24, so just 24. So we want to find a factorization of 24 into two factors whose sum is 11. And since we have a positive number that we're trying to factor and a positive number that we're trying to add up to, that means that the factorizations that we should look at here involve only two positive factors. And so we can just kind of run through the list. This isn't necessary to do. If you can realize which two factors of 24 add to 11 right away, then you can kind of skip doing this. But we could say, okay, 1 times 24, 2 times 12, 3 times 8, 4 times 6. And that would be kind of all the factorizations we could look at where both factors are positive. And then we would check, okay, well, 1 plus 24 is 25, so we don't want to use that one. 2 plus 12 is 14, so that doesn't quite add to 11. But then 3 times 8, so 3 plus 8 is going to be 11. So these are going to be our numbers for n and m. So we can go ahead and rewrite 11x as 3x plus 8x. So let's rewrite our quadratic expression as x squared plus 3x plus 8x and then plus 24. And then we want to do our two groupings. So for our first grouping, we could do x squared plus 3x. or plus 8x. We just want to make sure that we don't group the two linear terms together. And then 8x plus 24. Okay, and so for our first grouping, x squared plus 3x, well, the greatest common factor between those two terms is just going to be an x. So we'll pull out an x from that grouping, and what remains is going to be x plus 3. All right, and then for our other grouping, we have 8x plus 24. And so the greatest common factor that we're going to be able to pull out between those two terms is going to be an 8, because 8x has an 8 and 24 has an 8. And that's kind of the only, it's the greatest factor that they have in common. So 8, and then what remains after we peel off an 8 from each of those terms is just going to be x plus 3. So this is good. The expression that we have remaining for each of our groupings is x plus 3, so it matches across each of the groupings, which is what we want. And since we have that, we can now kind of essentially use the distributive property in reverse and group up the factors that we pulled out from each grouping as the two terms for our other binomial factor. So x plus 8 will be our other binomial factor. Then x plus 3. All right, for our second example, we have y squared plus 3y minus 10. So again, we're going to be like, okay, a is equal to 1, b is equal to 3, and c is equal to negative 10. Okay, and something I want to point out, which makes the AC method kind of even quicker than using the quadratic formula to factor a quadratic expression, is so what we can observe from the previous example is that the two numbers that we came up with, 3 and 8, were exactly the numbers opposite the variable x and our two binomial factors. So we had x plus 8 and x plus 3. So whenever the leading coefficient is 1, so whenever a is equal to 1, once we figure out our two numbers from the AC method, that is the two numbers n and m whose product is equal to a times c and whose sum is equal to b, we can go straight to writing our two binomial factors. It's just going to be y plus n, in this case, since our variable is y, times y plus m. So we just take our two numbers from the AC method and we just write them opposite the variable in our two binomial factors. And we can only use this shortcut though when a is equal to 1. When a is different from 1, we're going to have to use the grouping method like we did in the previous example. But here, since a is equal to 1, we'll go ahead and avail ourselves of this shortcut. So let's figure out our two numbers for the AC method. So a times c here is equal to 1 times negative 10, which is negative 10. And b is equal to 3. So we want to find a factorization of negative 10 into two numbers whose sum is a positive 3. So since we have a negative number for the product and a positive number for the sum, this means to us that we should look at factorizations where, since one factor is going to have to be negative and one's going to have to be positive, where the larger factor in terms of absolute value is going to be the positive factor. So such factorizations would be like minus 1 times 10, which is going to give us, well, a positive 9 for the sum. So that's not quite a positive 3, so let's keep looking. And then we could look at minus 2 times 5, and that would be really all the factorizations we could look at here, at least that we would be interested in. If we check the sum, negative 2 plus 5, well, that's going to be a positive 3. So these are two numbers from the AC method, And according to the observation that we just made about the shortcut, we can go straight to writing our two binomial factors as y minus 2 times y plus 5. And if you don't trust me that we can just go straight to doing this, you can always double check using the grouping method, and you will find the same two binomial factors. All right, so on to example 3 now. Here we have the quadratic expression z squared minus 4z plus 3. So a is once again 1, b is equal to -4, and c is equal to 3. So here, a times c is equal to, well, just 3. And since we want to find a factorization of a positive 3 into two factors whose sum is a -4, we're going to want to consider factorizations where both factors are negative. And luckily, since 3 is a prime number, there's only one factorization, or one such factorization for us to consider, -1 times -3. And of course, if we check the sum here, that's going to be a -4. So using the shortcut, we can go straight to writing our two binomial factors. They're going to be z minus 1 and z minus 3. And not that it comes up in any of these examples that we've looked at here, but if you are trying to use the AC method, and if you're not sure if it'll work for a given quadratic expression, because like I said, it doesn't exactly work for all quadratic expressions, only when the quadratic expression is like factorable over the integers, like ours have been. So if we notice, the numbers across each of our binomial factors are always integers in each of these factorizations. So if you're ever able to not come up with two numbers whose product is a times c and whose sum is b, what that tells you is that the AC method fails, and so you will have to use the quadratic formula to instead figure out the two binomial factors. All right, and on to our fourth example. So here we have 3m squared plus 5m minus 2. So a is equal to 3, b is equal to 5, and c is equal to -2. So here we won't be able to use the shortcut, so we will have to go back to using the grouping like we did in the first example. So a times c is going to be equal to 3 times -2, which is -6. So we want to find a factorization of -6 into two factors whose sum is going to be a positive 5. So since we're looking at factoring a negative number, we are going to want to look at factorizations where one factor is negative and one is positive. And since we want those two factors to add to a positive 5, we want to consider factorizations where the larger factor in terms of absolute value is the one that's positive. So such factorizations would be -1 times 6 and -2 times 3. And if we check the sum, -1 plus 6 is going to give us a positive 5, so that's going to be the two numbers we use for the AC method. And here, again, we have to use grouping, so we're just going to break up the middle term 5m and instead write -m plus 6m. So that'll give us our four terms that we can put into groupings of two terms, or into two groupings of two terms. So 3m squared minus m plus 6m minus 2. And then we can group the first two terms together, so 3m squared minus m, and then plus 6m minus 2. And then we want to pull out the greatest common factor between the two terms in each grouping. So for 3m squared and m, the greatest common factor is just going to be m. So we'll pull that out, and what remains is going to be 3m minus 1. And then for our other grouping, 6m minus 2, so the greatest common factor between these two guys is just going to be a 2. And when we pull out a 2 from 6m and minus 2, what we're left with is also 3m minus 1. So we can once again use that distributive property in reverse to say that we have, for one of our binomial factors, m plus 2, and for the other one, 3m minus 1.